Welcome, everyone. Thank you for coming to my talk on building agentic AI systems. And I'm going to talk about how we're evolving our SaaS systems from transactions to goals. So before I sort of get started, I'd love to just get a show of hands of people who have, how many of you have actually deployed an agentic AI system in production? Very small number, a couple. And how many of you are developing one that's not quite in production? And then everyone else, are you just trying to understand what this new world is all about? Okay, got it. Okay, well, that's pretty much what I expected. So just a little bit about me. For the past couple years, I've mostly been working around AI, advising a handful of companies and venture capital firm. Some of these things I've actually, some of the slides you show, I actually have blogged about, actually, working in collaboration with Wing Venture Capital. Before that, I was an entrepreneur. I started a company called Ambassador Labs, and that actually, we created two CNCF projects. One's telepresence, the other one's emissary ingress. And then before that, I worked at a bunch of cybersecurity companies, Duo Security, Rapid7, and Red Hat, and which is not cybersecurity, and Ars Digital. So anyway, so that's just a little bit about me. And in honor of sort of Van Gogh, this is an AI-generated version of me, sort of Van Gogh-ish style. Okay, so I want to start by talking about SaaS versus agentic systems. So we're all familiar with SaaS systems, right? So if you go to booking.com, there's a website, and you enter in sort of where you're going, some travel dates, right? And if you think about sort of fundamentally a website like booking.com, it's, first of all, it's transaction-oriented, right? And what I mean by that is there's a predefined flow with a clear start, which is here's some information, and a clear end, which is I've actually booked this flight. It's deterministic, right? The same inputs will create the same outputs. And it's this GUI-driven interface. There's all these forms and buttons that you click through. And ultimately, you are driving the execution. So if you don't fill in any information, the website doesn't do anything. Once you fill in some information, the website does something, right? And the technology or architecture behind all this that's made this all possible, hopefully everyone here is familiar, is the long and beloved N-tier web architecture, which we've adopted and evolved over the last 3 decades, maybe longer, who knows, right? So agentic systems are very different, right? Instead of being transaction-oriented, they're goal-oriented. Users are communicating the intent, right? Not the specific sequence of steps that you're expecting it to execute. And as a consequence, the interface is actually very different. You see much more of a conversational interface because conversations, whether they're audio or just typed out, is a lot easier to communicate goals than forms and buttons, right? The third thing about agentic systems is that they're stochastic. So if I give it the same input, the output isn't always the same. It will vary. It will generally be the same, but it's not always exactly the same. And finally, I would say the defining characteristic of agentic systems is that the system figures out how to achieve the goal. It's autonomous. And the magic technology behind agentic systems, of course, are large language models, right? So OpenAI has GPT-4o, GPT-5, O3. They have all these sort of names. There's Llama and Claude, right? But the magic behind that enables agentic systems are these large language models. And so what exactly is a large language model? Well, the way I think about a large language model is it's really just a brain. It's not the full system, right? The model itself is a set of weights. So if you ever download an open source or open weight model, like, say, Llama, and you sort of look at that file with the appropriate viewer, you'll just find it's just vectors and vectors of floating point numbers. That's all it is, right? And as a consequence, if you think about it, right, it can't do anything. It's just a huge, gigantic pile of billions and billions of numbers, and it represents a trained neural network that generates outputs from inputs. And around these LLMs, people build products or agents, right? ChatGPT, of course, is the canonical example of this, or GitHub Copilot and Cursor. And the way this all works is you add memory, tools, workflows. These are what the products actually add. And generally speaking, it's what I think a lot of people think about when they think about LLM. But the thing to remember is that LLMs, the purest definition of LLM is it's just a pile of numbers, right? It doesn't do anything. And as a consequence, when you're building an agentic system, the properties or the limitations of LLMs really shape how you design these agents. So an LLM is stateless. It doesn't remember the conversation. So when you ask ChatGPT, or I should actually clarify, when you ask GPT-4.0 a question and say, whatever you want to ask it, and it gives you an answer, and then you want to clarify and follow up, what's happening behind the scenes is the ChatGPT product is actually sending the full conversational history back over to the LLM, so the LLM actually can remember that context. So that means, in general, when you're implementing an agentic system, you need some sort of memory system. The second thing is, as people who've experienced LLMs, is they're very high latency. And so with an agentic system, you typically need to layer in an asynchronous durable workflow. So in other words, just because you ask an LLM a question or you give it a prompt and it gives you a response, it might take a little while. And so if you're using a classic synchronous deterministic system without sort of an orchestration, there's a good chance that somewhere along the line there will be a failure, and then you need to be able to resume where that failure actually starts. And so this is why there's sort of, especially in the agentic world, there's the rise of the popularity of agentic workflow systems, which I will talk a little bit more about later in this presentation. Stochastic outputs. So I just talked about how the same inputs into an LLM does not always create the same outputs. And so as a consequence, you can't just use a classic testing system. You need to use an evaluation system. You need to be able to evaluate how good your actual outputs are in order to figure out if your agentic system's any good. An LLM doesn't understand what truth is. It has a bunch of facts, some of which might be correct, some of which might be incorrect. And so it's incumbent upon you, when building an agentic system, to supply relevant facts and knowledge. The other thing about LLMs is they're context limited. They can only take a finite amount of context before sort of running out of room, right? It's just like all of us, we have a working memory. If I tell you too much information all at once, you're just not going to remember anything. So hopefully you'll remember something from this presentation. And so it's incumbent upon you to actually prioritize and compress that knowledge within the context window so that agentic system is able to make good decisions. And finally, like I said before, an LLM is just a pile of numbers. It can't act. So as an agentic system designer, you have to wire in tools and APIs for it to actually do something. So just to recap, right? So SaaS systems, transaction-centered. Agentic systems are goal-centered. We go from a deterministic world to a stochastic world, forms and buttons to conversational interface, user-driven execution to autonomous execution. And the last thing I would like to point out, though, is that ultimately, an agentic system is a distributed system. Just like a modern SaaS system is a distributed system with databases and queues and APIs and services, all this sort of stuff running in the cloud, right? You still have all those things, and then you layer in a large language model system, a memory system, you have additional tools. You're building a distributed system. So everything you know about the problems with distributed systems, the architecture of distributed systems is still very germane and relevant when you're building an agentic system. You just have to keep these other four things in mind. So let me talk about how you actually design agentic systems. So the way I think about an agentic system is there's an overall sort of reasoning loop conceptually. And that reasoning loop starts with the first step, which is what I call perceive, where you're actually bringing in context from your conversational history, facts, whatever, and you're actually supplying that to the LLM so the LLM can actually think about it. Once you've assembled that context, you send it to the LLM. The LLM actually thinks and reasons and creates a plan. And then with the plan, the LLM actually can observe and evaluate and maybe adjust that plan based on circumstances or additional information. And then finally, the LLM, or the agentic system, I should say, will actually perform some set of actions, right? So it might actually officially book that flight. It might actually query another agent, et cetera. So, and I would like to say this is more of a conceptual loop, and I'm going to talk about each of these phases in a little bit more detail. So in the perceive step, like I said, LLMs are stateless. They rely entirely on the context you provide it. And the term of art now that's gaining a lot of popularity is this term called context engineering. And context engineering is the art, mostly art, some science, of assembling all the context you need to give to the LLM so it can make the appropriate decisions that you expect it to make, right? So you typically start with your historical context. So this is your conversational memory, the state, so whatever the current conversation is, maybe conversations you've had in the past, right? You also then give the LLM a sense of what its environment looks like. In particular, if you want your LLM to call additional tools, you need to tell the LLM, hi, you have these tools that you can access, and these are the APIs to these tools, these are the schemas to these tools, whatever. The third thing, third type of context you typically provide an LLM is real-time data. So an LLM has what's called a knowledge cutoff. So it finishes its training on January 1st of this year. Anything that's happened after that, it has no idea. So it has no idea what the weather looks like. It doesn't know what the stock price looks like. So those are all good examples of real-time data that, depending on what you're trying to do, makes sense to actually send to the large language model. Additional facts, right? So a lot of these facts, you know, it might know sort of general sort of facts that you might find on Wikipedia. But another great example is if you're developing a corporate-specific agentic system, maybe you want to send it all your documentation, right? Or you might have corporate policies. All those things are facts that augment the context. And the last thing is what I would characterize as macro goals and constraints, right? So you may have particular policies in your company or a brand that you want the LLM to actually communicate. And so there's some macro level context and guidelines that the LLM should actually follow. So the accumulation of all this and figuring out what's relevant, what's not at any moment in time is what is called context engineering. So we now have context. We send it to the large language model where it thinks, right? And I'll talk a little bit more about what thinking actually really means in this context. And it produces a plan. Integrates all this perceived information and says, okay, this is what I'm going to do. So for example, maybe I have a travel agent. It's like, well, given the budget, I'm going to check Monday to Wednesday flights. They're usually cheaper. Verify hotel availability and share the options with the traveler. That's the plan. So I have a plan. The LLM needs to observe and evaluate it. So the way it does this is you might run some trial steps, right? So it might query a database. It might call an API to get more information about flight availability or whatever, right? And based on that, it may actually update and modify that plan. And it turns out, based on the plan, there's no affordable hotel options for those dates. So the original plan doesn't work. And we're going to look for Thursday through Friday flights instead, verify the budget still holds, and update the traveler with some options, right? So the LLM has observed and evaluated, reflected on that plan, created a better plan, and once it's made that plan, it will actually then act. So with act, we take these API schemas, which is part of the context, and we can actually ask the LLM now to execute the plan. And one of the common techniques that happens is the LLM can actually produce a structured output. And this is the interface typically for a large language model to go between sort of just text and actual execution. Because I previously said an LLM can't execute anything. So what the LLM will do is it will produce text in a predefined schema that you give it. In this case, this looks something like JSON. And when it's in a predefined schema, that is the way you can actually translate it. We hopefully all know how to parse a predefined schema, and then we can actually execute that. And so what you're doing here in the act phase is you're saying, don't just give me text response, because in whatever programming language you're using, you can't just parse a text response and conduct action on it. You're actually giving a schema, constraining the output to something that the rest of your agentic system can actually expect, and then you actually use that as input to actually execute. So just to recap, we're going through this loop of reasoning where we gather context, we think about it, we then sort of evolve and evaluate that plan, and then we act on that plan. So I said at the beginning that this is a little bit more of a theoretical construct. It's a mental model for how you should think about building agentic systems. And in practice, the lines between each of these steps is actually a little bit blurry. And in fact, there's actually this big debate going on, which I call the weights versus workflow debate. So on the weights side, you have people who are advocating saying, don't worry, it's one giant sort of thing. Just send all this context to our AI, and we're going to make our AI so smart that you don't need to think about all these other steps, right? Our AI will automatically sort of self-reflect and think about the plan, et cetera, right? And sort of OpenAI, I think, has been the most prominent advocate of this supermodel, we're building AGI sort of world. On the other side of the world, we have companies and people who are advocating for more of a workflow-centric. They're saying, you know what? It makes more sense to break this reasoning loop into discrete steps, right? There's the perceive step, there's the think step, and after each step, we may want to run a little bit of deterministic code as part of a workflow. And the advantage of this is it lets us sort of better understand and reason about how the system does it. I mean, it's just decomposability, right? Breaking something, a big problem into smaller chunks makes it easier to reason. And probably LangChain has been probably the most prominent advocate of this, and there's sort of this little sort of debate going on. Anthropic, as another prominent AI company, sort of a little bit in the middle. They actually say, well, you know what? We're trying to make our AI systems very advanced as possible. But the reality is workflows are still necessary. And what's happening recently is OpenAI, I think, even though they're trying to train their models to be the be-all, end-all, they're sort of recognizing reality. And if you look at sort of the OpenAI SDK, for example, they've just partnered with Temporal, which is a workflow system. So sort of, I would encourage people not to just sort of blindly just shove everything into the OpenAI API and cross your fingers and hope something good will happen. I think you probably want to sort of stay sort of in the middle or think about workflows depending on your application. So I just talked about the agentic reasoning loop. I talked about this weights versus workflows debate. And now I want to talk about how you actually build and the stacks that you actually need. And so there are 3 stacks, actually, that you need to build an agentic system. It's no longer a world where the LAMP stack is sufficient, right? You need 3 stacks. The first is the LLM training stack. So it's the stack you use to train and fine-tune a large language model. You need this inference stack, which basically takes all these weights and numbers and actually runs the thing. And then you need something actually, your agent runtime stack. So I'll talk about each of these 3 stacks. So how do you actually build an AI? So this is obviously like 25 talks in one, but I'll just distill it to one slide here. So the way generally AI works at a very high level is you start with all this raw data, right? So this could be books, it could be code, it's stuff on the internet. And then you go through a process of training this, and that process takes all this data and converts it into tokens, and then from tokens you convert them into weights, and you have these massive GPU clusters, and this takes lots of systems engineering. It takes hundreds of millions of dollars in GPU time, and lots of computer scientists and months of tuning. Once you have the training, you create a foundation model. So this is a general purpose LLM like GPT-4o or Claude, DeepSeek, Meta has Llama, right? So you have these foundation models. And then at the end of this, you can then do what's called fine tuning. You can take these foundation models and adapt it to your domain, right? Whether it's, I want to create my business is, Figma actually has a fine-tuned model that's really good at building user experience UIs, right? Or if I'm a cybersecurity company, I might build a cybersecurity LLM. So the foundation model takes sort of specialized data, and then it sort of starts with the fine-tuned model takes specialized data from your domain and uses it for additional training, so your foundation model becomes extra good at whatever domain you're giving it. And the reality is that most of us, I would expect in this room, are not going to be building foundation models. If you are, you should be giving this talk and not me. the reality is you'll probably be fine-tuning. And so that's sort of the caveat I would give around how I'm thinking, or I'm presenting this LM training stack. It's really around how you fine-tune a large language model. I'm assuming you're starting with a foundation model. And how does this work? Well, you start with this data acquisition. You get whatever data you need for your domain. And then you prepare that data, and you clean it up because data is generally messy. Then you run a whole bunch of experiments on that data. And then after you run all these experiments, each experiment you're training, you're evaluating, you're adjusting the parameters, and with each experiment you're evaluating sort of the results. And the way to think about this entire world is there are different tools in each of these spaces. So, and I'm not going to go through all these tools, but generally speaking, there are tools for data acquisition. There are tools. Pandas is a very popular open source tool for, I mean, I'm sure half of you have heard of Pandas, right? You can literally just load data into Pandas and just run a lot of data manipulation to clean it up. Experiment tracking, training, evaluation. And all of these steps are typically orchestrated using a pipeline and training orchestration tool because because you're going through all these different steps, you want it to be deterministic, you want to be source controlled. So you're going to use something like a Flight or a Dagster to do all this. The thing I want to emphasize is when you're going through this process, it's very experimental, right? So you basically develop an intuition, you try some stuff, and then you have to measure to see if it worked. If it didn't work, you try some other stuff. There is no sort of do this, do that. It's much more of an experimental mindset. The other thing I want to mention is that if you are thinking about doing this using open source, the open source ecosystem actually is very robust around fine-tuning. And I can tell you that you can fine-tune a foundation model very successfully using a pure open source stack. And in fact, I think most companies actually do this, start with an open source stack. You may end up sort of needing to upgrade, especially when you get to extremely large data volumes. But I would say all these things highlighted purple are open source projects, some of which like Flight and Kubeflow are part of an LF ecosystem, whether it's LF AI and data or LF or I don't know. There's so many foundations. Okay, that's the training stack. So how do you actually run an AI? So you download all these weights. It's just all these numbers. And if you think about it, there's a process that you follow to actually get an AI to do something. So you typically start with an input or a prompt. So you ask it a question. You translate that input into numbers. That's called tokenization. And so the quick brown fox, here's a vector of 4 numbers. You convert that text to tokens. You then run the model. And so for each token, you're doing a matrix multiplication against billions of parameters. And it produces this very complicated output, right? And then after you run the model, you generate after you do the matrix multiplication, it generates a list of probabilities. And from that probability, there's some algorithms, but you basically pick sort of the highest probability token, and then you convert that token back into text. This running the model thing is hideously expensive. This is why NVIDIA stock is worth as much as it is, because people have an insatiable appetite for GPUs to run the model. And so this entire process is called inference, and in order to run this, you need an inference stack. And this is what the inference stack ecosystem looks like. It was very complicated to do a build, so I didn't do a build. So I'll just walk through the stack right here. So you typically start with GPUs, and you can get GPUs from a variety of folks, whether it's one of the hyperscalers like Azure, Google Cloud, Amazon, or you can get GPUs from a dedicated GPU provider like CoreWeave. On top of that, I've got a bunch of GPUs. I need to orchestrate them because I don't want to manage each of them one by one. And so Kubernetes is the default orchestrator, but there's some other folks who like Slurm or SkyPilot. And then on top of Kubernetes, with a pile of GPUs, I need to run an inference engine. The most popular one is vLLM, which is actually a CNCF project, or not CNCF, an LF project. But there are other open source options like TensorRT, SGL. And this is where it actually is taking the process of taking a token, tokenizing, or taking a prompt, tokenizing it, running the matrix multiplication, giving you the output. Because this is a very intensive process, most people, when you start getting to scale, you also deploy what's called a key value cache. This is very distinct from a Redis or Valkey. Key value, this is actually a term of art around sort of LLM inference, and so there's some open source projects around this. And then finally, you have an orchestration routing layer. So typically, when you get a prompt that comes in, it needs to get routed. If you run different models, you need to make a decision on which model to route to, and so there's another layer on top of that. Because what I just explained is actually very complicated, of course, there are now integrated inference stacks. So ByteDance created this project called AI Bricks, which is powered by vLLM. NVIDIA has this project called Dynamo, also powered by vLLM. Anyscale has Scale, and BentoML has their own thing, also I think built around vLLM. And then if that's still too complicated for you, you just want an API, you can actually run and go to a Fireworks or Together to actually just upload your own model, and it will actually just run it for you. So on the right-hand side, you have the least amount of control, but it's the simplest. The left-hand side, you have the most amount of control, but it's by far the most complicated. And then highlighting, but you have lots of open source options. There's no open source GPU that you can really use. But all these other things, you could actually build a fully open source stack for inference if that's what you want to do. So that's the second stack. Third stack, the runtime stack. So I talked about how LLMs shape agent design, and so I'm not going to go through this all again. And as a consequence, you also need technology to actually run your agent. And so again, this is typically sort of what I characterize as your agentic runtime stack. You start with an AI inference stack, right? So that's what the previous slide. So you might run Llama or DeepSeek on vLLM with Mooncake as your KV cache. You then need a durable execution layer, whether it's temporal or Akka or DBoss, one of these technologies, to really make sure that when your agent runs, it actually runs to completion, handles failure in a cohesive way. Then on top of the durable execution layer, you have agentic frameworks, right? LangChain and Llama Index, but there's a whole bunch of Microsoft has this project called AutoGen, which basically help you build and code to LLMs and take care of a lot of the nitty-gritty stuff around prompt engineering, context engineering, that sort of thing. This is starting to get complicated. On top of this, you then need to interface with different systems. And there's sort of three different types of systems. The first one is memory. And there's some dedicated memory providers. You also will see that some of the agentic runtime frameworks also integrate memory, which is why it's sort of bumped up there. You also will have knowledge systems, whether they're vector databases like Pinecone or Weaviate, or just traditional databases like Snowflake. And then the last thing you typically have is, I'm trying to introduce this term called actuators, which are tools, right? Tools are actuators. And actuators or tools are technologies that let you the LM actually do stuff. And the reason why I actually like actuators is because calling them tools suggests that they're just APIs. But if you look at something like Blender MCP, so Blender is a 3D visual rendering language. You can literally type into Claude, build me a house with like 10 rooms, and it will just literally output Blender, and then you can actually get a 3D rendering of that house, sort of all in real time. And so it doesn't seem, it's not just a tool, it's sort of a broader, I think there's sort of a broader ecosystem of technologies and capabilities that are being added. So I sort of came up with this term actuator. So this slide is probably the most complicated and messy slide, and I think this is because this agentic runtime stack is still very much evolving. We see, companies like Akka are moving from durable execution and agentic frameworks. You see LangChain and Llama Index have introduced their own durable execution frameworks, and so they're moving into durable execution. So exactly how this is all going to shake out, the only thing I can tell you is this is most likely going to be out of date within a year. Oh, yes, and these are the ones that I would characterize as fully open source or have open source solutions, even if they're commercial offerings on top of them. Okay. So I talked about the agentic reasoning loop. I've just introduced 3 different types of stacks that you need to actually build agents. And I want to just talk briefly about what modern agentic systems look like. So modern agentic systems tend to be multi-agent. And when I say multi-agent, that means they have multiple different agents doing different things. And the reason for this is that it's really critical as you scale up an agent, there's only a limit typically to how much a single agent you can typically do. And so a very common pattern now is to have a lead agent that actually develops a plan, and then using that plan, it delegates that work to execution subagents. And what happens, though, is when you start going to this architecture, you end up with your workflow itself is stochastic because you don't always know which agents are going to be run in what order. It also makes the execution, it's a distributed system on steroids because now you might have dozens of different processes and agents running around that you need to coordinate. They might run for a really long time, right? And so this is sort of your typical, this is a sort of diagram where you have the planner agent, it makes a decision, it delegates to these executor subagents. These executor subagents create results, and then you finally aggregate all those results into a final result. And these executor subagents might run for hours or days, depending on the task at hand. So this is what I characterize as a more modern, sort of sophisticated system that you would probably want to look at as you sort of run out of horsepower with a single agent. The other point I would want to make is that every single agentic system that I've seen deployed successfully, they have very good evaluation systems, right? Because the thing is, with stochastic systems, you need to create repeatable results, even as components change, right? You might be updating your workflow or your model, your input data is going to vary, right? And so you need to measure a bunch of different things, and you want to measure those things both holistically end-to-end as well as each step. And so what's really important when you're starting to build an agentic system is I would recommend you start by building an evaluation system, right? And that's going to force a whole bunch of difficult conversations around how do we figure out what's good, right? Because it's not just, well, we want the agent to book travel. Okay, well, yes, of course. But how do we figure out if that travel booking was actually good? And then you have to start defining what good means, and then you have to figure out how you actually measure these things. And it turns out to be a very complex conversation. And so how do you think about evaluation? Well, there's no sort of one sort of silver bullet around evaluation. But here's a very simple framework here. So on the y-axis here, I have how much operational cost you have in an evaluation system. And the x-axis, I have the signal strength, how much signal it actually returns. And so human review. So if, again, in my travel agent example, if I have a human travel agent review every single one of them, obviously this is the highest cost because I'm not getting any, the computer's not doing that much, right? But it, in theory, gives me the most accuracy. A step down is a canary or shadow workflow where I actually duplicate all the questions that are being asked to my production system to my new system, and I can somehow compare those results. This is still really expensive, but because I'm literally doubling the cost of inference because I'm not only running a production system, I'm also running a shadow system, and I'm running every single question twice. But of course, it gives me very high signal around how well I'm performing. Offline suites, so I might have a set of standard sort of inputs that I've carefully curated and have humans label, and that's actually a really good strategy to give me a sense of where things are. And then finally, people start to calibrate additional large language models to actually measure and compare sort of the results, right? So you can have a large language model and say, and this is actually a very popular use case actually for OpenAI. So OpenAI turns out to be quite expensive to run in production, but they have very good models. So a lot of people will actually use OpenAI and say, here's some answers to this question. Scale this answer on a scale of 1 to 5, right? And that can actually help you get a sense, and it's relatively affordable. The signal's not quite as good as some of the other techniques. But there are always trade-offs. And so what I would recommend as you start thinking about your system is, once you figure out what is good, you need to employ a variety of strategies to actually measure what is good. Okay, home stretch. So the number one thing when I talk to enterprises and companies deploying agents is trust, right? Because if they can't trust the agent, because we're giving it autonomous execution capabilities, they're not going to deploy it, or you're going to deploy it in very limited, in a limited fashion. So I have this concept of the trust triangle, and so I think there are three things to consider when you're deploying agents. The first one is capability. Can it actually do the job? The second one is consistency. Will it do it reliably, right? And the third is containment. Can it be trusted to stay within the safety boundaries, right, that I've established, whatever those boundaries may be? And if you can actually establish these three things and communicate with the powers that be in your company, that you have a strategy for all three of these things, then I would suggest that you've gone a long way towards creating trust. So from a capability standpoint, and I'm just going to talk a little bit about some strategies that are emerging around how to manage these things. So LLMs are quite powerful, but at the end of the day, they're pattern recognition machines, right? And so they get a lot of things wrong. So an emerging thing that's actually coming up, especially that's being very popular in agentic systems, is these reasoning models. So reasoning model is an LLM that's gone through additional training to do some additional thinking, and you actually deploy this model in an inference stack that will also give it the ability to take on more time, which means more GPU power, to think about an answer. So some of you may have encountered this most recently with GPT-5, where if you give it a really hard question, it might say, I'm thinking for a little bit longer, right? Or you can get a quick answer. And if you think about it intuitively as a human, if you get 5 minutes to answer a question versus you're asked to answer a question right away, your performance tends to be hopefully better on the 5-minute answer than the right away answer, right? And so this is a technology and approach that I'm seeing folks use very strategically. You can't use a reasoning model for everything because it's higher cost, it's much, much slower, but it turns out for certain kinds of applications, it's very powerful and can really improve your capability. So consistency, right? So how do you get the same inputs? How do you verify that the outputs for your agent are actually reliable? So these are all challenges. And so eval first development, right? What I just suggested, right? I know we've talked for decades around test-driven development. I think eval first development is super important as you start adopting agentic systems, right? Because you want to start thinking about how do you evaluate these systems, how do you actually score and observe and monitor all this. And so there's no sort of, like I said before, no silver bullet around evaluation, but there's a lot of work you can do to make your system easier to evaluate, which will give you much more confidence that it's actually consistent. The last thing is containment, and I think this is the biggest area of exploration and innovation that's happening right now, right? Because new attack surfaces, whether they're malicious or not, are emerging. Your traditional threat models around AI well, there's no traditional threat model around AI. So your traditional threat model for your computer and systems is radically changing the face of AI, right? So there's a whole bunch of stuff that's actually happening around cybersecurity. What approaches people will actually adopt, remains to be determined. But there's a whole bunch of, OWASP has introduced their top 10 for LLM applications. Google has its own threat framework. And so I think a lot of this will become much more apparent over the next few years. Okay, just to kind of wrap things up. I just went through a whirlwind of stuff around how we're evolving SaaS systems, which are transaction-centered, to agentic systems, which are goal-centric. And so sort of the takeaways I would say is you first need to adapt to large language models. That's the first thing. To build an agentic system, you need to recognize that LLMs are stateless, they're high latency, and you need to handle that behavior. The second thing is you want to build the loop and not just think about it as a call, right? So think about that perceive, think, observe, and evaluate and act loop. The third thing is leverage these stacks. There's been a whole bunch of open source projects for training, for inference, for runtime, that will get you a very long way to building an agent, right? And you can actually even probably use ChatGPT or Claude to actually build a lot of this stuff. And then as you start running into challenges, you want to scale by going to multiple agents and thinking about your evaluation workflows. And then to engineer trust, right, which is a big part, what I would say, of building agentic systems, think about your capability, consistency, and containment. So thank you for coming. Happy to take questions, and if I run out of time, you can ask ChatGPT. Yes?
That's great talk. Thanks so much. So I'm wondering why you didn't mention temperature, because when you set it near to 0, you get a more deterministic response. Have you any thoughts on that?
So the question was why I didn't mention temperature. So temperature, because if you set the temperature to 0, you get a more deterministic response. So temperature is this parameter that you can actually send to a large language model, and to like the gentleman's point, it controls the variance. It's certainly a technique. What I have found is that and I think more specifically in testing scenarios, I do think it's a good idea to set both the seed and the temperature as a way to kind of explore, as a way to measure. The problem is it's very much not real world, and it really limits your LLM's ability to kind of think. It doesn't sort of reflect sort of the variance that you're really looking for in an LLM, if that makes sense, right? So you want the LLM to actually be able to handle a wide variety of things, and you also want it to output different things depending on different situations, and so that's generally speaking not something I generally bother with. So, sure, yeah. So I think the question is, if we add more thinking time, do we increase the stochasticity of the system? Is that your question? Yeah, and I think we are, right? But I think there's some benefits to it because you get, in theory, a better plan or better accuracy. So so I think the mindset that I have is just embrace the stochasticity, right? And don't try to control it. I think it's better to actually just measure and account for it in your system as opposed to trying to minimize it, right? It's kind of like, distributed systems theory. If you try to sort of engineer systems to never fail, your system's still going to fail. And so it's much better to kind of engineer a system that assumes that these components are going to fail and build resilience into it. And so I think that's sort of the mindset that I would encourage people to take. And that probably is a more cohesive answer to your temperature question. Yes? Oh, I thought you raised your hand. Any other questions?
I've had a conversation with OpenSearch, and they've just joined the Linux Foundation, and it strikes, it can be used as a layer in the stack because they can do RAG, they can do fine-tuning, they've got MCP connecting to the LLMs. Have you any views on that?
So the question is about OpenSearch, and honestly, I've never heard of OpenSearch, so I have no opinion. Yeah. Okay, well, thank you everyone for coming. All right.